but not only, as I said. So Jin actually got his PhD at the University of Tokyo back in 2002. And then from then he moved to the National Astronomical Observatory in Japan for 3 years. Then he was a postdoctoral researcher and then later a senior postdoctoral researcher at Caltech in Pasadena. And then since 2009, if I'm correct, you became an assistant professor at the Department of Physics and Astronomy of Stony Brook University. So, and I don't know if I missed something important, but that's more or less what I recall. And if you want to add something else.
Yeah, I think that's enough.
So again, thank you, Jin. That's a really big pleasure for all of us that are organizing this meeting. And please go ahead, you can share your screen, okay. And we'll have time for questions at the end of the talk.
Okay. Thank you very much for the introduction. And yes, Armando and I, and also his wife Carmen, spent quite a good time in Pasadena when we are a postdoc together. So anyway, yeah, I work on, back then I was in Owens Valley Radio Observatory Group, and later it became Kalmar Observatory. We combined 2mm arrays to make a single array system. And I want to give you some idea of what it was back then. So today's talk is about molecular cloud, and I picked this topic because there are some recent trend, which is, I think, in my view, is sort of against what we established before. And I want to give you, since there are a lot of master students, I believe, I want to give you some caution about the recent trend. So the recent trend, there are discussions about lifetime of molecular clouds, and there are big papers, very important and very good studies, and they claim that cloud lifetimes should be very short, like 10 or even 30 million years. And I want to give you the context of this time scale later. But the topic, the discussion actually started in 1970s, before all of us, any of us were born, probably, before my time, before I was born even. And there are a lot of rich material in the past and a lot of very thoughtful discussions about the lifetime of molecular. So I want to make this talk a little bit provocative, and also include a historic aspect, because there are very important physical considerations in this topic. And I hope that especially young astronomers get some sense of what we are talking about. There are a lot of approaches toward this problem, GMC lifetime, but here I take an approach from large-scale galactic structures, large-scale considerations. So it's going to be provocative, and also a lot of historic papers cited. Okay, and I hope that you can make your own judgment. So let's go through what molecular cloud first. So giant molecular clouds, you probably heard about it in lectures. Concentration of gas, molecular phase of gas. And if you look at the Orion constellation, for example, these are 3 stars along the belt and arms of Orion and legs. And this part of the Orion constellation and this part of the Orion constellation, we find a lot of molecular gas. And this is carbon monoxide 120 emission observations. And we typically use carbon monoxide molecule to trace molecular component of the gas. There is a huge concentration here. And if you look at the densest part, do you see my cursor? Yes?
Yes, we do.
Okay. Yeah, so if you look at the huge concentration of most dense part of molecular cloud, and here, we find the star-forming region. For example, Orion Nebula, I think, is around this concentration of gas. But this whole thing is called the molecular cloud. Here's another example. The disk of the Milky Way is running in this way. You can see dust rains, running in this way. And here is one molecular cloud, Pipe Nebula, the other molecular cloud, Rho-Ophiuchus molecular cloud. There are a lot of molecular clouds in the plane of the Milky Way. There has been a survey of molecular cloud in the Milky Way, and there was a significant, two significant surveys in 1980s. And they characterized typical size of molecular clouds. Let's say the diameter, the typical one is about 40 parsecs. So it's a huge structure compared to individual stars. Velocity dispersion from Doppler shift measurement is something like 4 kilometers per second. And these are very cold structure, 10 Kelvin or so in gas temperature. Thermal velocity width is only 0.2 kilometers per second, but the observed velocity width is 4 kilometers per second. So it's highly supersonic, very turbulent structures. So the gas are moving around very rapid pace and collide to each other and form stars. The typical mass of molecular cloud is 4 times 10 to the 5 solar masses. So it's a very massive structure. Typical surface density is 170 solar mass per square parsecs. And typical volume density is 300 H2 particle per cc. So this is relatively high density compared to the average density of the interstellar medium in the Milky Way. The average is like 1 particle per cc. And within the molecular cloud, it's 300 particle per cc. Molecular clouds are important because we are interested in star formation, and star formation occurs mostly, actually all in molecular clouds. And here is an infrared image of the Orion constellation from Acari satellite, my own country from Japan, Japanese satellite. If you look at the concentration of CO emission or molecular gas, the dust emission is very bright because they are heated by young newborn stars. So molecular clouds are site of star formation. I think many of you, since this is a colloquium of Armando's group, many of you probably study about galaxies and star formation in galaxies. When you really want to learn about star formation, we also need to think about how molecular clouds form and how long they survive and how they die. That gives you the physics of star formation for galaxy evolution. If you look at individual molecular cloud, in this case, Perseus molecular cloud in the Milky Way galaxy, relatively nearby from the sun, only 140 parsecs away from the sun. This is just the central part of the molecular cloud. The bulk part of the cloud have average density 300 particles per cc, as I said. Star forming parts are very localized within molecular cloud. And for example, this is a famous star forming region, IC 348 and B1 and LGC 1333. The whole thing is molecular cloud, and only tiny patches are dense enough, 10 to the 4 or 5 particles per cc, and those are the locations where stars are forming. So when you think about star formation, you need to think about how to assemble huge amount of mass of molecular cloud in molecular cloud, and then you need to make small dense clumps to actually form stars. Okay, so this is the entity we are talking about. There is a new survey of the Milky Way disk in carbon monoxide emission CO120 survey by the Novayama 45-meter telescope. I will mention about your telescope, IRAM 30-meter later. And we are actually, Japanese are actually jealous of IRAM 30-meter. I will tell you that later. But this is from the Novayama 45-meter telescope. So this is the emission distribution of carbon monoxide emission distribution in the Milky Way disk. Just the northern part of the sky, the northern part of the disk. And if you zoom in, you start to see concentration of molecular gas, and these are molecular clouds. There are many molecular clouds across the Milky Way galaxy or any other galaxy. We can see molecular clouds and molecular gas in nearby galaxies, and this is M51 Hubble Space Telescope image. And even in optical images, we can see dense concentration of gas as a dust rain. So these dark parts are the concentration of the interstellar medium, and you can find molecular clouds, and you can get a sense of the distribution of molecular gas and the molecular clouds in the galactic disk. This is carbon monoxide CO120 emission map of M51, which we took almost 10 years ago. And the gas is concentrated, molecular gas is concentrated along spiral arms. But these fuzzy things or blobs, they are all real in these images. There are a bunch of molecular gas in between spiral arms. But there are concentration. They are mostly concentrated in spiral arms. You've probably heard about the new survey with Alma, and there's a big one, FANG's Alma CO221 survey. The PI is Eva Schindler, and Adam Leroy is playing a big role in this survey. And they are observing something like 50 galaxies, including archival data. They have something like 70 galaxies observed in CO221 emission. And I must say that we had been in a gap period between results from previous telescopes, and we are getting results from Alma telescope recently about a large-scale molecular gas distribution in nearby galaxies. So I can say there will be a lot of good results coming soon. It already started to come, and we will see more in the near future. The resolution, the spatial resolution and sensitivity that this huge Alma survey achieved is something like 100 parsecs in physical scale. Again, the average diameter, typical diameter of GMC in the Milky Way is 40 parsecs. So 100 parsec is not enough to actually resolve individual GMCs, but it's very close. It's only twice larger than the diameter of GMCs. The sensitivity is something is around 10 to the 5 solar masses. Again, the typical GMC in the Milky Way disk have 4 times 10 to the 5 solar mass. So they can detect, the Alma can now detect typical GMCs in nearby galaxies. And there are many of them observed recently. And this is an image from 2021 paper. We use CO, carbon monoxide emission, to trace molecular gas in the Milky Way or nearby galaxies. And I want to explain a little bit about CO excitation. So we need to excite CO so that we can see emission from CO. The excitation is triggered by collisions with H2 gas. So CO molecule collide with H2, and that increase the spin state to higher energy level. And once you get up, and then it will naturally comes down to the lower energy level. And when you do that, you emit 1 CO 120 photon. The spontaneous emission is governed by Einstein coefficient, and I think you probably learned about it already, or you are going to learn about it soon. The actual amount of emission we receive depends on the amount of the rate of collisions. If you have higher density, then there are more collisions. So you excite CO, more CO to a higher energy level, and then they come down to the lower energy level and emit 1 photon or many photons if you have many CO excited. So the balance between the collisional cross-section and Einstein coefficient gives you the critical density for CO excitation. And if you calculate that in case of optically thin condition, and then you get critical density something like 3,000 particles per cc, which is 10 times denser than the density of molecular cloud. But we see a lot of CO emission from molecular cloud. It's very strange. You need 10 times higher density to emit CO. What's happening in molecular cloud is something called a photon trapping. molecular cloud has a huge amount of gas, so it's optically thick in CO 120 or 221, lower transition of CO. So because of the optical thickness, not all photons escape from molecular clouds. Many of them are actually trapped within molecular clouds. So the effective spontaneous emission rate decreased because a lot of photons, large fraction of photons, are absorbed locally. If you think about the geometry of molecular clouds, and then we can calculate this escape fraction, beta, with optical depth. And there are a few ways to do it, depending on the geometry, but typically, in generally, beta is roughly proportional to 1 over the optical depth. So if you have very optically thick condition, let's say optical depth of 10, then the fraction of CO escape from molecular cloud is only 10%. And effectively, that will reduce the Einstein's A coefficient. So if you use that reduced A coefficient, and then we get critical density of 300 particles per cc or so. So it's a very strange situation. If you have molecular gas in molecular cloud optically thick, then you need only 300 particles per cc to emit CO. But if you go outside of a molecular cloud, then you actually need even 10 times higher density to excite CO. In other words, if we find CO in nearby galaxies, and then the emission must be coming from molecular cloud or something like molecular cloud with the density of 300 particles per cc. So in case of nearby galaxies, even thanks Alma survey, it does not resolve individual molecular clouds. And there's a confusion problem. We often encounter confusion problems, but when we detect CO, then it's coming from molecular clouds, which are not resolved, but you need that kind of density and optical thickness to emit CO. Good? Yeah. Okay. I want you to visualize that we are talking about some dynamic system, and this is numerical simulation, including stars and gas and star formation by a friend of mine, Baba et al. 2017. Blue color is for atomic gas, and white or yellowish color is molecular gas. And they really move within the disk of the galaxy. They coagulate, and then they expand in some of our locations. Okay, so this talk is about the lifetime of molecular clouds, and I want to give you the context of it in large scale. And there has been a lot of debate since 1970s, and I don't think we have converged. There's a range of suggested ages. For example, shortest lifetimes of molecular cloud is something like 2 or 3 million years, suggested. Longer ones are longer than 100 million years. And there are somewhere in between, something like 20 or 30 million years as the suggested lifetime of molecular cloud. And of course, the Milky Way galaxy or any other galaxies are rotating around its center, and the rotation time scale, let's say at the position of the sun, is 230 million years. So if you think about these clouds, suggested cloud lifetime in the context of galactic rotation, if it's short, like 2 or 3 million years, that means clouds just form and die immediately before it even moves at all within the disk of the galaxy. If it's 30 million years, then it's roughly the time scale of spiral arm passage. So clouds form in spiral arm and then die when they exit from spiral arms. That's roughly the time scale in the context of large scale motion. And if the cloud lifetime is 100 million years or longer, and then the cloud forms somewhere and then move within the galaxy or significant distance, okay? In other words, if we find some kind of motion of molecular structure within the galaxy, if molecular structure moves from one location to the other location in the disk of the galaxy in a significant way, the lifetime should be, long, at least 30 million years to go across the spiral arm, and something like 100 million years to go through interim regions. There is a standard picture of cloud evolution, and that gives you the answer. Most textbook shows you this picture of density wave theory, which is governed by density wave and also stellar feedback. What you hear in class or in textbook or read in textbook is something like this. So the gas is mainly atomic in the interim regions, and they get compressed in spiral shocks due to density wave, and the shock convert atomic gas into molecular gas, form molecular clouds. But once you form molecular clouds, then star forms immediately, and stellar feedback is significant enough to destroy the parental molecular cloud. So after the spiral arm passage, you find atomic gas again. Is this what you are teaching in your university? Yeah, you're right. I mean, in the textbook, we find this picture. And as I said, this talk is provocative, and I take any criticism, but I'm going to advocate that we should change the picture from this to this. In my view, there are a lot of small molecular clouds in between spiral arms in the interim region, and they coagulate and becomes massive molecular clouds. But because of the strong shear motion across spiral arms, they get shredded apart and become smaller molecular clouds. The gas stays molecular in the interim region, and then in spiral arms and in next interim region, the gas, cloud size changes from small to large, large to small, but the gas is in molecular clouds, and the gas stays molecular. And I even say that we actually need to combine the two to explain all the observations in the past. In the inner part of this galaxy, the main part of this galaxies, then this dynamically driven evolution of molecular clouds, small to large, large to small, is the dominant mechanism of molecular cloud evolution. But if you go to the outskirts of galaxies, then we find a lot of atomic gas in between spiral arms, and they get compressed, becomes molecular cloud in spiral arms. So textbook and your teachers are, of course, based on some observational evidence. And there are a lot of observational evidence which support the textbook picture. And if you look at nearby molecular cloud, in this case, a lupus star-forming region, and this is carbon monoxide emission distribution, molecular cloud distribution. And this is the same area, the same contour, but with OB stars and pre-main sequence stars, young stars on top of it, plotted on top of it. There's a spatial anti-correlation. If you find young stars, massive stars, and then the gas around them are photo-dissociated, so we don't find much molecules. So we actually see molecules being destroyed or molecular clouds being destroyed. If we look at nearby open clusters, young ones, and since they are open clusters, we can age them, and then look around them and see if you can find parental molecular clouds. And if you do that exercise, you find molecular clouds around young clusters up to 3 million years, but all the young clusters, but all the clusters beyond 3 million years, you typically do not find molecular clouds. So this is the argument for very short lifetime of molecular clouds. Young clusters, once young clusters form, and then they immediately destroy parent molecular clouds. So there's a reason for short lifetime. We can go through statistics of molecular clouds, and in this case, they looked at the large Magellanic cloud, surveyed the entire large Magellanic cloud, identified molecular clouds and then classified them based on the stage of star formation. There are a lot of type 1 molecular clouds which do not have any star formation at all. And there are type 2 which have molecular clouds and H2 region associated to it. And type 3 which have H2 region and young clusters next to it. And if this is the evolutionary stage of molecular cloud, no star formation, H2 region, and H2 plus young clusters, if you count all of them, the population ratio, the count ratio, gives you the ratio of the time scale of each evolutionary stage. And now you know the lifetime of H2 region, something like 10 million years. So if you use that as a scale, then you can get the whole scale of cloud evolutionary stage. So 6 million years for the first stage, 13 and 7. And if you add them together, you get GMC lifetime of 20 to 30 million years in the Large Magellanic Cloud. Similar exercise, similar study was done in other galaxies. Messier 33, for example, Miura et al. Got 20 to 40 million years at the lifetime of GMCs. And recently, Fang's survey, the one I mentioned, got something like 10 to 30 million years with the same concept, but modified method. M33 is relatively small, maybe the smallest spiral galaxy, H1 dominant. So if you map out H1 distribution in M33, you can find spiral structures in H1. So the color behind is H1 distribution. And that are molecular clouds distribution. So if you look at them, molecular clouds are on spiral arms. That gives you a sense that, okay, molecular clouds form in spiral arms. And when they get out from spiral arms, they get destroyed. So their lifetime should be crossing time scale 20 to 30 million years. So there are a lot of evidence, there are a lot of supporting observations for short lifetime. And that's why the textbook is written. How about the Milky Way? Of course, we live in the Milky Way, so it's very difficult to disentangle the distance to it. And I think you've seen this graph. So the background is the Milky Way picture, and these lines are isovelocity contour. When you observe, let's say this is the sun, and this is the galactic center, and if you observe 30 degrees away from the galactic center, along the line of sight, there are a lot of gas, and at each location, because they are following galactic's circular rotation, they show different Doppler shift along the line of sight velocity. So this is a velocity longitude diagram. The vertical axis is longitude, and the horizontal axis is longitude, and vertical axis is velocity. If you look at just 30 degrees direction, and then you find lot of gas at different velocities, and each velocity corresponds to each isovelocity contour. The problem is in the inner galaxy, if you find gas at 40 kilometers per second in redshift, there's also the other component further out, and the gas here also have 40 kilometers per second velocity. So this gas and this gas are on top of each other in the data and mixed up. And this is called distance ambiguity. We do not have distance ambiguity if you look at outer part of the disk of the Milky Way. So we can say something about the outer part. So if you look at the longitude velocity diagram again, zooming up to the outer part, we find Perseus spiral arm gas concentration. This is CO120 emission, by the way, so tracing molecular gas distribution. And there's a fainter but definite spiral arm pattern, a sequence of molecular gas in the LV diagram. But we don't find much molecular gas in between. And that probably means that molecular clouds exist only on spiral arms, but if you go outside of the spiral arm, then the gas phase is H1. And that's why we do not detect molecular gas in the outer spiral arms. And that fits to this textbook picture. Atomic gas in the interim region, molecular gas on spiral arm, then the atomic gas in the next interim region. There are a lot of interferometric studies early on, before many of you master students were born, probably. It was very difficult to observe nearby galaxies. That's a part of the reason why the textbook was written in the way it is. So this is a comparison of Owens Valley CO120 map of M51 and with the other interferometer, BIMA interferometer map. This map found this significant CO emission component in the interim region, but this map didn't. It was very difficult to discuss about emission in the interim region because of the nature of interferometry. If I have more time, I'm happy to explain about how interferometer works, but I need to skip that. So because of that confusion, about 10 years ago, we observed M51 again with Kalmar interferometer and November 45-meter telescope. And this is the map we got back then. As I showed before, there are spiral arms, molecular spiral arms, and in between, we find molecular emission. So it's not entirely atomic in between spiral arms. We can identify molecular clouds. The sensitivity was 3 times 10 to the 5 solar masses. So it's slightly below the average density of the average mass of molecular clouds in the Milky Way. But within that limitation, what we find is in between spiral arms, we find lower mass molecular clouds. And on spiral arms, we find molecular clouds, but they tend to be higher mass. So we seem to be seeing something like this. Less massive molecular clouds in between spiral arms. And when they get into spiral arm, they get coagulated, becomes larger molecular cloud. Pulse survey, PDBI, and also IRAM 30-meter telescope observed the central part of M51 at much higher resolution than our observations and much higher sensitivity also. And they could characterize the mass distribution or mass function in the interim region and spiral arms. And what they found is similar to what we found at lower resolution. In the interim region, you don't find much massive molecular cloud. But if you go to spiral arms, you start to find massive molecular clouds. There is a coagulation of molecular cloud, large in spiral arms, small in interim regions. So this seems to support this new picture that I've been advocating, or different pictures that I've been advocating. Old people sometimes want to brag about what they've done. So I just want to show you this because this is one part of there are many reasons why Japanese are jealous about IRAM 30-meter, but this is one reason. November 45-meter telescope doesn't have a heater on the dish. So when we encounter snow, then we have to sweep snow from 45-meter dish. So this is me sweeping snow from the 45-meter dish. And I heard that you guys have heater, so you just turn it on and then the snow melt, so you don't need to go through this. But this may remind you of something very Spanish, right? So every time I sweep snow from this gigantic 45-meter dish, I always think of Don Quixote fighting against windmill. Okay, just a joke. So I said that things are moving. And we can run a very simple numerical simulation, just put spiral density potential of stars and put gas in it. What we see is the gas get into spiral arms, but because of the shear motion along spiral arms, the gas tends to make blobs, large, massive molecular clouds because of the instability along spiral arms. And these blobs get shredded apart and extend into the interim regions because of the differential rotation. And naturally, if you make a massive blob on spiral arm, and if you shred them apart, you make sparse structures in the interim regions. So the picture is like this. Small clouds become massive, and massive clouds shredded apart and stretch in one direction. So it's like a chain of small molecular clouds expelled towards the interim region. And that's the picture I have. We can trace the distribution of large molecular particles with PAH emission. PAH do not emit photon by itself. It needs to be shined by the background radiation. But when you see it, you can see how molecular gases are distributed. And if you look at interim regions, there are filamentary structures sticking out from spiral arms. And these looks like the sparse structures we can find in numerical simulation. With PAH, we cannot characterize the mass, but if we detect them in CO, we can measure the mass. So this is just part of the data we looked at. And this is spiral arm, this is another spiral arm. And if you look at the root of or blobs on spiral arms, we find something like 10 to the 7 solar masses. And if we measure the mass within each filamentary structure or spars, we find something like several times 10 to the 6 solar masses. So it kind of makes sense, massive blob, massive GMC on spiral arm, and if you shred it apart in the interim region, then the mass conservation is right. So the reason why I've been advocating that we need to change the picture, or we need to rewrite the textbook, a lot of small molecular clouds because we see them in the data, and massive molecular clouds on spiral arm because we see them in spiral arm in the data. And these massive ones become smaller, shredded apart, become smaller molecular clouds, again, because we see them. It's very simple. If this picture is right, then we shouldn't find much atomic hydrogen in interim regions, right? And we can check that. And what we can do is compare CO map to trace molecular gas density and H1 21 centimeter map to trace H1 gas density. H1 data typically do not high with spatial resolution, so we have to smooth the CO data, unfortunately, but we can do it. With 1 kiloparsec resolution, roughly, we calculate something called molecular fraction, which is the fraction of molecular gas over the total amount of gas, molecules, and atoms. Ionized gas component doesn't have much mass, so we can ignore them. We can neglect them. If you look at this, especially the central part, spiral pattern, which is clear in molecular gas distribution, almost disappeared in the fraction. Even in between spiral arms, the fraction is high. So the gas is staying molecular, and we found the molecular cloud in higher resolution CO data. And this is the reason why at least in the inner part of the galaxy, we should change the picture. Small molecular clouds get coagulated on spiral arms, becomes massive, but they shredded apart, become smaller molecular clouds, and the gas phase stays molecular. But if you look at the outer part, then we do see molecular fraction goes down in between. So the traditional picture, textbook picture seems right if you go to the outskirts of galaxies. Since we have master students, I think we should use brains. So let's think about it a little bit, the physical background of it. What does high molecular fraction really mean? And this is the reason why I said all the literature is actually very important, because they get into very simple physics. So let's think about this donut, a band, annulus, around the center of the galaxy. The gas, let's assume that the gas is in pure circular orbit, so the mass within this band is conserved. The gas becomes atoms or molecules, go back and forth in between. And if we measure the total amount of atomic mass, gas mass and molecular gas mass, and if we know the typical lifetime of H1 gas and typical lifetime of H2 gas, and if they are in equilibrium, and then this equation should hold. So total H1 gas mass divided by the lifetime of H1 gas gives you, the destruction rate of H1. The total molecular gas mass divided by total molecular gas lifetime is destruction rate of H2. And two should be balancing against each other to maintain the equilibrium. From that, the lifetime of H2 gas is equal to this ratio times the H1 lifetime. Now, in M51, we find more H2 than H1, at least in the inner 10 kiloparsecs of the disk. If H1 becomes H2, when it encounters spiral arm, if you have two spiral arms, then the H1 destruction or formation time scale is roughly the half of the rotation time scale, something like 100 million years. So this is 100 million years, and this is larger than 1, or much larger than 1. Cloud lifetime or H2 molecule lifetime should be longer than 100 million years. So there are people who say molecular gas lifetime is 20 million years or 30 million years, but this simple argument and simple observation tells you that molecular gas lifetime should be very long, 100 million years or longer. You may notice that I'm kind of mixing things up because I switch between molecular gas lifetime and molecular cloud lifetime. They are different things, right? And there is one philosophical question which I cannot really answer. I just give you my position is this. So I'm saying that small clouds become massive and massive clouds become small clouds. When we say molecular cloud lifetime, should we say this is the cloud lifetime or this is the cloud lifetime? This H2 gas lifetime is this lifetime, long lifetime. And I take this lifetime as the lifetime of GMC because when we say GMC lifetime, we are always thinking about the readiness for star formation. If you say cloud lifetime is 20 million years, then most people think that 20 million years is the only time the gas can form stars. So to give you the right idea in the right context, the context that most people are interested in, I think we should call this long lifetime the gas, the duration that the gas stays in some molecular cloud. That should be the cloud lifetime. You can take your position, but this is what I'm talking about as the cloud lifetime. How about Milky Way? And I said Milky Way is difficult because what we can measure is the line of sight velocity. And there are always two positions which have the same velocity and we cannot separate them. But if we can measure a quantity which is distance independent, and if we assume cylindrical symmetry, And then this position and this position should have the same quantity. Or if you keep looking at this isovelocity contrast, you realize that this position and this position are confused in our measurement, but at the end of the day, their distance to the galactic center are the same. So if you want to measure radial dependence of molecular fraction in the Milky Way, then you don't need to solve the distance ambiguity problem. So we take H1 data, northern hemisphere part of the Milky Way and southern hemisphere, carbon monoxide emission, and that gives us H2 density. And from those, we can calculate molecular fraction in velocity longitude space. Each velocity and longitude point corresponds to one galactic distance, galactocentric distance. So we can just take this and convert that to the radial profile of molecular gas fraction, which is this. In the Milky Way, which is basically the same as in M51, the molecular fraction is very high, almost 100% at the center, and it goes down to almost 10 or even 0 around the sun. If the gas becomes molecular on spiral arm and then atomic in the interim region, then these points should go down close to 0, but they don't. We notice a couple of things. In the inner, let's say like 6 kiloparsecs or so, molecular fraction stays high, above 50%, or even 70 or 80. The width, the scatter of it, gives you arm interim contrast, and it's only something like 20 to 30% change. So there is a change, but not much. The gas stays molecular even in the interim region in the Milky Way, which is the same as M51. So again, in the Milky Way, the gas is molecular in interim region, molecular in spiral arms. How about the outer part of the Milky Way galaxy? If you go to the outer part, this is the same plot, molecular fraction as a function of galactic radius. Outer part, the fraction, the average fraction is low. And occasionally you find this huge bump. Molecular fraction goes up. Corresponding structure in LV diagram, velocity longitude diagram, are these. And these are the known locations of spiral arms. In spiral arm, in the outskirts of the Milky Way, the gas is mostly molecular, so molecular fraction is low. But when they get into spiral arm, it becomes molecular. So we need to synthesize the two pictures. Inner part of the Milky Way, the gas stays molecular. And if you find CO emission, as I explained, it should come from entity like molecular cloud with a density of 300 parts per cc or greater. But if you go to the outskirt, then the gas seems to follow the textbook picture like that. So as I said, this talk is provocative, and you may take some part, you may not take some other part, it's up to you. But I'm trying to explain the very basics of this argument, what we see and what we do not see. I'm just saying that we see molecular clouds in interim region in nearby galaxies and in Milky Way. We do not see atomic gas in the interim regions. So that simple fact should tell us something very basic. Good? I think the good thing of Don Quixote is there's certain truth to it, right? Behind what he says. He looks crazy, but some occasion he is right. Of course, the research field is advancing, and we use Alma. And I want to show you. Yes, any question?
No, please go ahead.
Okay. Yeah, so I want to show you some preliminary results from Alma observations. So Alma, of course, gives our, makes our life much easier. They do observation, no more snow sweeping. Not the time of Don Quixote anymore. We have 12 meter antennas and 7 meter antennas, and also total power antennas. Combining those data is already a research field, and I worked on it, and I even have a paper just on the combination technique. And as I said, a huge important fungus survey just released data recently, and there will be a lot of important results coming out from fungus survey. And to complement that, we decided to do, the fungus survey have resolution 100 parsecs and sensitivity 10 to the 5 solar mass of molecular cloud. And to complement that, we decided to go to the other direction, just to look at one galaxy, but much higher quality compared to the fungus survey. And we picked M83, which is very similar to Milky Way, so we can easily compare the two galaxies. And here is a map, CO120 map of M83, and I haven't shown this to that many people yet. So you guys are one of the first people outside of the collaboration, of course. The sensitivity is 10 times higher than the fungus survey, but just one galaxy. The resolution is 40 parsecs, so twice higher than fungus survey. And this is the resolution, the diameter of GMCs. We spent 20 hours, just 20 hours of Alma time just on this galaxy and 180 hours of the compact array time. So it's a huge amount of observational time investment in a single galaxy. This is roughly like a third of fungus, which observed 80 galaxies, but we are observing just one galaxy. Do we have time?
Yeah, well, I mean, if you still have a couple of slides, that's fine.
Okay. Okay, so I have more than a couple of slides. So let me skip this. Now I have a couple of more slides. Yeah, so we can calculate molecular fraction in M83. Again, we don't have very high resolution H1 data yet. So we have to smooth Alma data to 30 arcsecond resolution, which is 650 parsecs. We find the same thing, high molecular fraction in the inner part of the galaxy, but it becomes low in between spiral arms if you go to the outskirts of the galaxy, which is the same as M51 or Milky Way. We can identify molecular clouds, and we find molecular clouds in between spiral arms, and massive ones are red dots along spiral arms, which is similar to what we found in M51. Small clouds coagulate, becomes massive ones on spiral arms. They're broken up to smaller ones in between in the next interim regions. So I think we really should change our textbook picture to this one. Okay, just a summary. So I started from many observations that support textbook picture. If you look back, most of them came from the observation of solar neighborhood, nearby molecular clouds, or very near dwarf galaxy like LMC, or relatively small spiral galaxy, Messier 33. We could even argue it's a kind of dwarf. But if you look at M83, M51, or inner part of the Milky Way, then we start to find that they are mostly molecular. The gas phase is mostly molecular, not much atoms because we don't see it. So that support long cloud lifetimes, including coagulation and fragmentation of clouds. So if you look back at the history, we started from something easy to observe and constructed this textbook picture. But if we look at different regions, more difficult regions which we can now observe, the picture seems like this, dynamically driven evolution. So we can rearrange these regions in terms of size, and relatively low density regions, small galaxies, the phase of the atom, dominant phase of the molecules, the gas is atoms. In those regions, feedback-driven mechanism seems right. But if you look at large spiral galaxies, dense region, the gas phase is mostly molecular, then the dynamically driven evolution seems the correct one. So we should synthesize them, and this is the final slide. So this is the summary of the whole talk. I hope I did better than Don Quixote in terms of convincing you. Okay.
Thank you very much, Jin. So we have time for questions. So please raise your hand in the Zoom participants panel so I can see if there is any question. I think Patricia has a question, so please go ahead.
With me. Thanks a lot. Very interesting talk. I enjoyed it. Well, you mentioned that briefly at the end, comparing the small galaxies and the big galaxies, but even between the big galaxies, I mean, you have different types of spiral arms, no? I mean, you have some that are like more density waves, but we also find some others that are like more, I mean, they are short-lived and they turn out dynamically the same as density waves. So I don't know, in your model, I mean, you should expect differences between these two types of galaxies. Is there something that?
Yeah, that's a very good question and very good point. Yeah, there are flow current galaxies, for example, other big disk galaxies, and we haven't looked into it yet. Yes, it's very curious how the evolution changes in that kind of situation. And Fungus survey have data of flow current galaxies, and as I said, I think two of different kinds of observations are complementary. I think by combining the two, we can get even better, more basic pictures of cloud evolution. So I stressed spiral arms and dynamical mechanism. There should be also some local fluctuation of density, and that should be able to make structure like molecular clouds even without spiral arms. And I think the question actually is the balance between the two, the local gravitational force perturbations and spiral arms, dynamical, large-scale perturbations, which is more dominant, and that could depend on the potential of the galaxy, so the type of the galaxy. That's some interesting vector that we should look into.
Cool. What about in the bar? Because I saw in some pictures that there's a lot of also molecular.
Yeah, so the bar part, at least in MET3, we find a lot of, well, it's mostly molecules.
Yes, yeah, a lot of molecular, and also very, very massive molecular clouds, no?
Yeah, right. So can I show? So this is the bar part. Do you see my screen?
Yeah.
Yeah. So there are a lot of massive molecular clouds along the offset ridges. What's surprising is even outside of those, there are molecular clouds. And what's interesting, but I didn't mention, is there seems to be a lot of molecular gas outside of the bar, which we didn't expect before. And because of the sensitivity, we are starting to see very extended emission. Around this spiral arm, for example, these emissions, they are real. And but we are not resolving individual GMC in this very extended component. But the density needs to be 300 particles per cc or so. So I think that there are small GMCs which we cannot resolve with the current resolution.
That is amazing.
Yeah.
Just the last one. What do you think mark the difference between the inner parts and the outer parts? Why in the inner parts the feedback is able to destroy the cloud and not in the other?
Yeah, that's also a very interesting question. We don't know yet. The important thing and interesting thing we should look into is, yes, the actual amount of feedback are used to drive interstellar medium. There is a discussion about where and how much feedback energy get into the interstellar medium, and many people say that feedback is enough to drive turbulence in the inner part. But if you go to the outer part of the galaxy, you don't have as many supernovae, for example, the source of feedbacks, but you still find turbulent velocity, supersonic velocity dispersion in the interstellar medium. How can we drive that? Is a question we don't know the answer to yet. So that's something we should look into more carefully.
Okay.
And with new data.
Is that related with internal pressure or something? In the inner part being higher, maybe. I don't know. No, I just think it out. I mean, people think this is due to the MF or this is due to, because otherwise, I mean, why would you have more supernovae in the center, in the outskirts?
Yeah, very good point. And in this talk, I didn't talk about star formation aspect of it at all, because I couldn't cover it within the given time. But individual cloud. This kind of observation is very important when you think about star formation and galaxy evolution. And if cloud lifetime is 100 million years, then most of the clouds are not forming stars. You need to trigger star formation in pre-existing molecular clouds. And that changes your thinking of the trigger of star formation. Because right now, with short lifetimes, you think that, okay, you form molecular cloud, and then immediately they form stars. But cloud lifetime is long, then you cannot do that. You really need to maintain cloud for a long time, and then somehow trigger it. And the triggering mechanism is the controlling mechanism of galaxy evolution. And we don't know the answer to it, but it's a very important question.
Yes, very interesting. Well, thank you.
Thank you, Beth. Any other question for Jin? Any, Anne? You cannot raise your hand. You can also speak out. No problem. You can speak up and make your question. Okay, I have a question myself, Jin. And it's, you told us at the beginning that, well, first of all, I should say that if you are the Quixote in this thing, I'm happy to be your Sancho Panza. You know, right?
Okay.
You convince me, so I'm happy to follow you in my donkey.
Oh, good.
So, no, the actual question is, you mentioned at the beginning that you can only see CO in giant molecular clouds. Okay, but it seems to me that that's a kind of catch-22. It's because you only see the molecular clouds when you have CO. So it's like, by definition, your giant molecular cloud, it has to have CO, because that's the way you detect it. So that means that in your internal region, there could still be a lot of CO that is basically the gas is not at that density, and because the CO is optically thin, you wouldn't detect it even with your highest sensitivity right now. So that in principle should actually boost even more the molecular fraction in the internal regions. So it will actually even give you more reasons to be the Quixote in this case. So what do you think about that? It makes sense?
So that's right. So CO dark molecular gas has been a topic of discussion for quite some time, in the past 10 years or so. Yeah, so in a relatively high metallicity environment, like these nearby significant spiral galaxies, in those situations, I think the suggested fraction of CO dark molecular gas is something like 30%. So that 30% may be on top of the discussion that I gave. The whole thing I discussed about is based on CO observations, so what we can see. And we see them, I can say that they exist. So that's the bottom line of this talk. But you are right. There might be about 30% more molecular gas that we may not be able to see in CO. And that, I think, even strengthens the argument.
Yeah, I mean, a potential counter argument will be, for example, the pH emission. But in that case, the problem is that your heating sources are so far away from the interstellar region that you might not see pH just simply because you don't have the interstellar radiation field. Is just too weak or too diluted to actually see the pHs. So again, even the counter argument has its own counter argument. So I think it's very interesting.
Yeah, and also the other one more thing we need to consider is H1 gas could become optically thick, and that hides some amount of atomic hydrogen. But the estimated amount of that is also like 30%. So everything I said have something like 30% error. But even then, I think the whole picture stays the same. I hit 30%.
Okay, thank you very much. Any other question for Santi? Please go ahead.
Yeah, I have a question. Well, first of all, very nice talk. I am not an expert on intergalactic medium, but I like a lot this topic also because of what I am working on. So it was very interesting. And my question is regarding the physical process of these clouds being from the coalescence to becoming maybe a single cloud and then breaking apart in some other, again, smaller pieces. And my question is the following. Is this process really bringing individual molecular clouds together, becoming a single self-gravitating object, and then becoming again several other clouds after going through the spiral arm that are not connected by gravity? Or is just because you have no enough resolution yet to identify a process that is just putting closer these small molecular clouds and then getting them apart again after passing through the gravitational potential? This because I think it is important, because if they really became self-gravitating, this will trigger star formation because you will have a deeper, larger density. But if this is only getting them closer, then maybe you are not triggering a star formation. No, I don't know which scenario is the one you are proposing, or maybe it's not resolved yet.
That's an excellent question, and I think everybody wants to know the answer to it. So if we do like typical analysis, like looking at virial parameter, comparing mass from luminosity and mass from virial calculation, and if they are around 1, then most people say it's self-gravitationally bound. And if we do that, yeah, we find most of these clouds around virial parameters of 1 are self-gravitationally bound. However, the mass from luminosity depends on the conversion factor, and that could have the error or uncertainty of even like a factor of 2. And if you are a factor of 2 away, then you can make gravitationally bound clouds to non-gravitationally bound cloud. So that's the dilemma we have. But if we go through regular analysis, as I mentioned, these clouds seems to be gravitationally bound.
Okay, so but if they became gravitationally bound, how you can destroy them after leaving the potential well of this panel?
Yeah, especially the big ones. So the big ones we find okay, so I'm just giving you my idea of how I can picture it, because I have no ways to really prove if they are gravitationally bound or not. The massive cloud on spiral arms, they are probably not gravitationally bound, or could be bound, but a small input of energy can unbound it, state around that. Otherwise, you are right, it's very difficult to break them apart to smaller pieces. On spiral arms, there's a shearing motion due to the stellar spiral potential, and a velocity gradient across a relatively massive cloud is almost comparable to the internal velocity dispersions. So that adds energy into the cloud, and that might be enough to shred them apart, unbound them. Of course, there are star formation and stellar feedback. If you make massive clouds, then inevitably massive star forms, and feedback from them may split them apart, but not destroying the gas, molecular gas into atomic gas. That's the other mechanism.
Good, thanks. So I can also think on a picture in where you can have both, no? Some of them will not become gravitationally bound and will leave the spiral arm without big perturbation, and some of them, depending on the convergence, they will become bound and allow triggered star formation. No? Maybe something like that is also possible. A bimodal scenario, no?
That is very possible. I think we can check that phenomenologically because we can identify star forming region in observations. So we should be able to compare local velocity field and location of star forming region and the structures around it.
Great, thank you.
Armando, you're muted.
Thank you. I was saying thank you, Santi, and thank you, Jin. And any other question or for Jin? Okay, doesn't seem to be any hand rising. So thank you, Jin, again for your talk. It was lovely. I love it. So I learned a lot, and I hope the rest of the audience also did. And so we will have another IPARCOS seminar, I think, next week. And I just encourage you to follow them. And well, again, thank you to everyone for attending to the seminar. Thank you again, Jin, for taking your time. And I hope you have a very nice day there in New York.
Thank you very much.
Thank you. Have fun.
Thank you. Well, we can clap at least.
We can clap.
Thank you.
The three of us, yeah. Thanks a lot.
Okay, next time let's see in person.
Sure.
Yeah.
Well, if you are coming to Marseille, I mean, you are not so far away. So
yeah, we can drive probably.
Yeah, you know, there most people is gone already. So there are many friends coming here to Madrid just to get drunk. I don't know anymore, but a few months ago we were so popular. So you can join them if you want.
Okay.
I'm not saying
like all the time.
That's an option. That's an option. So well, Jim, thank you very much. It was lovely. I really enjoyed.
Oh, thank you very much.
And it was I would say it was the right balance between academic and new results. And I think actually many of the people are actually master and PhD students of our group. So I'm sure they learn a lot and they enjoy the talk. So thanks again.
Okay, great.
Okay.
Okay. Yeah. Thank you very much.
Hello to Noriko and have fun.
Bye.
Bye bye. Santi, ¿paras tú el YouTube?
No, porque te he vuelto a hacer host. Has sido host durante toda la reunión, ¿eh? No te has enterado.
Ostras. Entonces la detengo ya. Bueno,
sí.
Esta última parte quizás la podemos haber quitado.
Me puedes recortarlo.
Sí, porque bueno, aunque si alguien aguanta hasta el final de las cuestiones, bueno, ya está, es parte de la familia, ya puede.
Bueno, muchas gracias a todos los seguidores en YouTube y a ver si va y nos da algún like o algo de eso a este vídeo y podemos hacernos un poco